Good day, this is Team Erbium, and this is a short crash course on titrimetric methods of analysis. To be in particular, we will be covering overview of complexation reaction and titration, chemistry of EDTA, complexometric EDTA titrations and its titration curves, overview of redox reaction and titration, and lastly, the various types of redox titration. Let us start with a brief overview on the complexation reaction and titration. The complex formation has many uses in analytical chemistry. This reaction can be described as a reaction that forms a complex compound. It is also known as the complex formation reaction. A complex is defined as a molecular structure that consists of a metal atom or ion in the center that is surrounded by ligands. The general equation of a complexation reaction is represented as M plus L will produce Ml, which in M is a metal and L is a ligand. Complexes generally form around a transition metal cation, and a bright color change indicates the formation of a complex. So why is complex formation reaction used in analytical chemistry? To be particular, complexes are colored and they absorb ultraviolet radiation. Its formation is often the basis for spectrophotometric determinations. Moreover, some complexes are sparingly soluble and can be used in gravimetric analysis. It can also be used for extracting cations, and lastly, these are used for dissolving insoluble precipitates. The truly remarkable growth of complex formation in analytical chemistry is forming chelates. The substance containing two or more donor atoms and forms ring structure with metal is called a chelate, and this property is called chelation. The chelated complexes are most stable than the non-chelated complexes because the more the rings in a complex, the more stable the complex is. Now, there are two types of chelating agents, the sequestering and the chelating agents. The sequestering agents are chelating agents that form water-soluble chelates. They are useful in removing objectional metal ions from aqueous solution, for removal of Boiler scale, and for removal of harmful radioactive metals from the body fluids. On the other hand, chelating agents form metal chelate precipitate, and they have many biological applications and are important in life processes. So why the formation of chelates is important in analytical chemistry? First, it is used as metal precipitants. It is also used in quantitative determination of a metal ion. The formation of chelates can also be used for the spot test for radicals, and it is also beneficial in gravimetric and volumetric analysis. Complexation reaction have many uses in analytical chemistry, and one of the earliest uses, which is still widespread, is in complexometric titration. In these titrations, a metal ion reacts with a suitable ligand to form a complex, and the equivalence point is determined by an indicator or an appropriate instrumental method. The formation of soluble inorganic complexes is not widely used for titrations, but the formation of precipitates, particularly with silver nitrate as a titrant, is the basis for many important determinations. Complexometric titration curves are usually a plot of Pm is equal to negative logarithm of the concentration of M as a function of the volume of titrant added. Usually, the ligand is the titrant and the metal ion is the analyte. Based on the given graph, why are multidentate ligands preferred for complexometric titration? Well, multidentate ligands offer the advantage that they usually form a more stable complexes than unidentate ligands do. Furthermore, they often form but a single complex with a cation, which simplifies their titration curves and makes endpoint detection easier. The precipitation titrimetry is based on reactions that yield ionic compounds of limited solubility, and argentometric titration is a type of titration with silver nitrate. The requirements for an indicator for a precipitation titration are that The color change should occur over a limited range in P function of the titrant or the analyte, and the color change should take place within the steep portion of the titration curve for the analyte. So there are three types of argentometric titration. That is the Moore method, Pahan's method, and the Volhard method. In the Moore method, sodium chromate serves as the indicator for the argentometric titration of chloride, bromide, and cyanide ions. Silver ions react with chromate to form the brick red silver chromate precipitate in the equivalence point region. The FANS method uses an adsorption indicator, an organic compound that adsorbs onto or desorbs from the surface of the solid in a precipitation titration. The adsorption or desorption occurs near the equivalence point and results in a color change as well as in the transfer of color from the solution to the solid or vice versa. And lastly, the Vollard method is one of the most common argentometric titration. In this method, a measured excess of standard silver nitrate solution is added to the sample, and the excess silver is determined by back titration with a standard thiocyanate solution, and this serves as the indicator. The solution turns red with the first slight excess of thiocyanate ion due to the formation of a red complex. Organic reagents are also used in forming complexes. To be in particular, it is useful in precipitating metals, in binding metals so as to prevent interferences, in extracting metals from one solvent to another, and in forming complexes that absorb light for spectrophotometric determinations. The most useful organic reagents form chelate complexes with metal ions. Another important application of organic complexing agents is in forming stable complexes that bind a metal and prevent it from interfering in a determination. And such complexing agents are called masking agents.
Now let's proceed in the chemistry of ETA. ETA stands for ethylene diamine tetraacetic acid, and it is most widely used as a complexometric titrant. As we can see in the structural formula of ETA, ETA molecule has 6 potential sites for bonding a metal ion, the 4 carboxyl groups, and the 2 amino groups, each of the latter with an unshared pair of electrons. Thus, ETA is considered as a hexadentate ligand. And next is the complexometric ETA titrations and its titration curves. So ETA is considered as a weak acid, so there are various species of ETA. As we can see in the ladder diagram of ETA, the species Y4 becomes the predominant form of ETA at pH levels greater than 10.17. It is only for pH levels greater than 12 that Y4 becomes the only significant form of ETA. And next is the complexes of ETA and metal ions. ETA combines with metal ions in a 1-to-1 ratio. So for example, silver and aluminum complexes. And here is one of the common structures for metal ETA complexes. So ETA behaves here as a hexadentate ligand in that 6 donor atoms are involved in bonding the divalent metal cation. So the ability of ETA to form complexes with metals is responsible for its widespread use as a preservative in foods and in biological samples. For equilibrium calculations involving ETA, we can use this equation where acid dissociation constant is equal to ETA anion over the total molar concentration of uncomplex ETA. And here is the sample problem involving that equation. And now let's proceed on the ETA titration curves. As we can see, the formation constant for the ETA complex of magnesium is smaller than that of the calcium complex, and this produces a smaller change in the P function in the equivalence point region. And take note, due to the higher formation constant, the reaction in calcium ion and ETA is more thorough, resulting in a larger change in the equivalence point region. So the shaded regions indicate the transition range for the areochrome black tea indicator.
So now I will discuss the overview of redox reaction and titrations. Redox reactions are fundamental in technology and natural processes involving changes in the oxidation states of reactants as electrons are transferred between species. From the burning of carbon to the oxidation of glucose in the human body, redox reactions play vital roles. Oxidation involves the loss of electrons or an increase in the oxidation state, while reduction entails the gain of electrons or decrease in oxidation state, often remembered with the mnemonic oil rig, which means oxidation is losing and reduction is gaining. Um, Redox reactions are important in our daily lives and underpin in many technological advances. From the combustion reactions that power fires to the electrochemical process in laptop batteries, redox reactions are fundamental to various aspects of technology. In this reaction, the transfer of electron between species drive chemical transformation, enabling energy production, storage, and countless other applications essential to modern life. Redox reaction involves the simultaneous occurrence of oxidation and reduction processes, with one species being oxidized while another is reduced. The five main types of redox reaction are combination, decomposition, displacement, combustion, and disproportionation. Um, First is combination, where the elements combine to form a compound with oxidation and reduction occurring together, while the composition, compounds break down into their component elements with oxidation and reduction processes reversed. And the displacement is where the elements replace each other in compounds, resulting in one being oxidized and the other is reduced. In combustion, organic fuels react with oxygen to produce carbon dioxide and water with oxidation of the fuel and reduction of oxygen. And this proportionation, some substance undergoes simultaneous oxidation and reduction, as in the case of hydrogen peroxide decomposing to produce water and oxygen. In redox titration, the concentration of an unknown analyte can be accurately determined by titrating it against a standardized titrant. For instance, the redox titration of unknown concentration of iron ions can be conducted using standardized solution of potassium permanganate as the titrant. In this reaction, potassium permanganate acts as its own indicator due to its bright color purple, while the iron ions solution is colorless. The titration endpoint where all iron ions have reacted is indicated by a slight remaining purple color in the solution, making it visibly distinguishable.
Now let us delve deeper into the various types of redox titrations. As discussed earlier, oxidation is the process where a species loses electrons while reduction involves the gain of electrons. These electron transfers are central to redox reactions. Redox titration is a laboratory technique used to determine the concentration of an analyte by conducting a redox reaction between the analyte and the titrant. It relies on an oxidation-reduction reaction, and it is widely utilized for determining the concentration of unknown analytes. In a redox titration, it is much more convenient to monitor the concentration of the reaction potential using a potentiometer, because the reaction potential directly reflects the progress of the redox reaction. This way, it provides a more accurate indication of the endpoint of the titration, making it easier to determine when the reaction is complete. Redox indicators, also referred to as the oxidation reduction indicators, are substances that undergo a noticeable color change at the endpoint of the titration at a particular electrode potential. The indicator signals the completion of the reaction. Various indicators are employed in redox titrations, and each is suited to different types of reactions and analytes. Let's now explore some types of redox titrations. Permanganometry is a type of redox titration involving the use of permanganates to measure the amount of analyte present in an unknown chemical sample. Permanganometry using potassium permanganate is widely regarded as the most cost-effective approach as it eliminates the need for an external indicator. It is often referred to as a method that has an autoindicator because the potassium permanganate used can change color by itself. The permanganate solution is a strong purple color. However, when it is used as a titrant and added to a solution of a reducing agent, the mixture tends to remain colorless till the equivalent point is reached. The endpoint is indicated by the very first drop of the excess permanganate ion, which gives the solution a permanent purple color. Permanganometry is typically conducted in highly acidic solutions, in most cases, in which this electrochemical reaction occurs. In this reaction, permanganate ions gain 5 electrons and are reduced to manganese ions, while hydrogen ions are present to maintain the acidic environment. This reduction process occurs with a standard electrode potential of 1.51 volts, and this shows that potassium permanganate is a very strong oxidizing agent. Potassium permanganate undergoes standardization against a standard solution of oxalic acid in the presence of sulfuric acid through a redox reaction. In this reaction, oxalic acid is oxidized to carbon dioxide, while potassium permanganate is simultaneously reduced to manganese 2 sulfate. The ionic equation involved in the process can be broken down into the reduction half reaction and the oxidation half reaction. And this is the overall ionic equation. To illustrate, at the start, when potassium permanganate is introduced into a conical flask containing oxalic acid, it results in a colorless solution. As oxalic acid ions are completely consumed, the endpoint is signaled by a pink color due to the excess of unreacted potassium permanganate. Furthermore, potassium permanganate reacts with sulfuric acid to produce manganese sulfate, which serves as a catalyst for the reduction of permanganate ions. As a result, the reaction rate is initially sluggish but accelerates as it progresses. It's important to mention that this titration cannot be conducted in the presence of strong acids such as nitric acid or hydrochloric acid, as they themselves act as oxidizing agents. This is due to the chemical reaction that occurs when hydrochloric acid reacts with potassium permanganate solution, forming chlorine, which is also an oxidizing agent, and this interference disrupts the accuracy of the titration process, which will render the results unreliable. Now let's move on to another type of redox titration, which is iodometry. Iodometric titration, an indirect method, measures the iodine amount used in a pre-titration step. This experiment is commonly employed to determine the amount of analyte used to make iodine, especially when assessing oxidizing agent levels in water samples. Almost all strong oxidizing agents can be estimated using this method. During iodometry, iodides react with oxidizing agents in acidic or neutral environments. Iodide, typically added as a potassium iodide, oxidizes into iodine while the other species are reduced by iodide. The liberated iodine can then be titrated using another solution, often a standard thiosulfate solution. We can perform another titration using the same mixture to measure the amount of iodine released. In this titration, we use the standard thiosulfate solution to titrate the mixture. To determine the endpoint of the reaction, starch is added as an indicator. Using starch as an indicator can help create a sharper color change at the endpoint. Initially, when iodine is present in the mixture, it imparts a dark blue color. However, as iodine is consumed during the reaction with thiosulfate ions, the dark color gradually fades away. Iodide is a mild-reducing agent because it readily undergoes oxidation to form iodine while losing electrons. Here are some examples of the reactions where iodide ions act as reducing agents. In each of these reactions, iodide ions are oxidized to iodine while reducing other species. The reaction with nitrous acid is often utilized in analytical chemistry to determine the nitrite ions in solution. By reacting with iodide ions, nitrous acid is reduced to nitric oxide, while iodide ions are oxidized to form iodine. The formation of iodine can be detected by a color change to allow for the quantification of nitrite ions in the solution. The reaction with bromate ions is commonly employed in environmental chemistry and water treatment processes for the determination of bromate ions in drinking water. Bromate ions are potential carcinogens, so their concentration in drinking water must be monitored. And by reacting with excess iodide ions, bromate ions are reduced to bromide ions, while iodide ions are oxidized to form iodine. The appearance of iodine indicates the presence of bromate ions in the water sample. For the reaction with dichromate ions, it is commonly used in organic chemistry for the qualitative analysis of alcohols and other organic compounds containing carbon-carbon double bonds. And this reaction serves as a qualitative test known as the Jones oxidation test. When an alcohol or a compound with a carbon-carbon double bond is treated with acidified dichromate solution, it is oxidized to a carbonyl compound to a carboxylic acid respectively. Simultaneously, dichromate ions are reduced to chromium-3 ions while iodide ions are oxidized to form iodine. The presence of iodine confirms the oxidation of the organic compound. Next, let us explore dichrometry. This type of titration involving potassium dichromate as the oxidizing agent is called dichrometry. This method is also particularly helpful in determining the concentration of substances that can be oxidized by dichromate ions in acidic solutions. In dichrometry, the orange-colored dichromate ions serve as the oxidizing agent, while the substance being analyzed acts as the reducing agent. The half reaction in the dichromate system is as follows. This chemical equation represents the reduction of dichromate ions to chromium-3 ions in an acidic solution. Dichromate titrations require an indicator. There are three indicators that may be used for the titration of iron 2 plus with potassium dichromate. These are diphenylbenzidine, diphenylamine, and diphenylamine sulfonate. The color change for all three indicators is green to violet. One common application of dichrometry is in the determination of the iron content in a sample, particularly in iron supplements or in iron ores to quantify the amount of iron. In this application, ferrous ions are oxidized to ferric ions by dichromate ions. For the determination of iron in an iron ore, the best indicator for this titration is diphenylamine sulfonate ion, which turns a deep violet color at the endpoint. In the initial stage of the titration, iron ore is dissolved in hydrochloric acid, where iron 3 is reduced to iron 2, and the solution is titrated with a standard dichromate solution. The starting sample mixture is clear and colorless, and as the titrant is added, it reacts with the substances being analyzed, and in this case, a compound containing iron, and it undergoes reduction, producing chromium-3 ions in the solution. Chromium-3 ions typically exhibit a green color, so the solution initially turns green. This reaction is represented by the following equation. At the endpoint of the titration, when all the iron in the sample has been oxidized to iron 3+, the slight excess amount of dichromate will oxidize the indicator. As a result, the solution changes color from green to violet. This violet color is attributed to the formation of a complex between the oxidized indicator, or the diphenylamine sulfonate ion, and the chromium 3 ions present in the solution. The indicator undergoes oxidative coupling and oxidation during the titration process, which leads to the formation of this violet-colored complex. Dichrometry can also be utilized in the determination of chromium-3 salt and chemical oxygen demand determination, where the organic matter present in the water sample is oxidized by the dichromate ions to form carbon dioxide and water. In conclusion, while we have delved into permanganometry, iodometry, and dichrometry, it's important to note that redox titrations encompass even more methods such as serimetry and bromometry. These techniques are significant in analytical fields due to their versatility and reliability when it comes to measuring the concentration of substances with oxidation reduction properties. Again, this is Team Erbium, and that would be the end of discussion for Analytical Chemistry CRTV Topic 007, Titrimetric Methods of Analysis Part 2.